In this video we're going to introduce the Moivre's theorem as well as present a partial proof. So here we're stating the theorem itself. It basically gives us a way of easily calculating the nth root, or nth power, I should say, of a complex number. So we'll begin by presenting an example. So if we've got z equals 2 cis pi on 3, and we want to find z to the power of 4 in Cartesian form, we can use the Moivre's theorem, firstly by splitting it out like this. Now we can simplify and then expand our definition of cis, draw a very rough unit circle, and replace cosine of 4 pi and 3, etc. by its actual value. To prove the Moivre's theorem, we begin by establishing two properties. The first of these properties concerns the modulus of complex numbers. So we're going to prove this property using mathematical induction. So as per usual, we need to establish the base case. So we want to prove that P1 is true. This one's very straightforward. The left-hand side and right-hand side are both equal to modulus of Z1. So it's easily proven that P1 is true. Next, we write down our inductive assumption. So assume that PK is true, giving us this property here. And we're going to use that to prove that PK plus 1 is true. So a typical inductive step in our proof. So we focus on the left-hand side, and we split that out into the product of Z1 up to ZK multiplied by ZK plus 1. Now we can use the property that we've established in a previous video to split that out. And we can also use then our inductive assumption. This allows us to prove that the left-hand side is equal to the right-hand side. So PK plus 1 is true. And then finally we wrap this up by making our inductive statement. Second property we're going to prove involves the arguments of a complex number as given by this property here. Again, we're going to establish this using mathematical induction. So again, we begin by looking at the base case. So proving that P1 is true. And this, as the previous proof, is very straightforward. Left-hand side equals right-hand side. We now assume that our inductive case, PK, is true. So it sets up our inductive hypothesis. We're going to use this hypothesis to prove that PK plus 1 is true. So as per usual, we focus on the left-hand side. I'll write that down. We group the first k terms together, and we're going to use our inductive hypothesis PK to rewrite that. Next, we can use a property that we established. So then we use a property that we established earlier. And now just rewriting our addition, we see that that's cis of theta 1 up to theta k plus 1, which is equal to the right-hand side. So therefore PK plus 1 is true. And then finally we wrap up our inductive statement. So having proven those two properties, we can then use the two properties to establish the Moivre's theorem in the case where n is a positive integer. So effectively we want to prove firstly that z to the power of n, or the modulus of z to the power of n, is equal to the modulus z all to the power of n. So we're going to use property 1 to prove this. And we're going to let z1 through to zn all equal z. We can then use that to expand out z to the power of n, which then allows us to use property 1 that we've established earlier. Next part of the proof involves looking at cis theta to the power of n. We want to establish that equals cis n theta. We're going to use property 2 for this, with theta 1 up to theta n equal to theta. So if we look at the left-hand side, we can expand that out to cis theta times cis theta n times. We can then use our property 2 to rewrite that as cis theta plus theta, etc., which is equal to cis n theta. If we combine these two proofs that we've just established, then effectively we've established Moivre's theorem in the case, again, where n is a positive integer. For those interested, you can look elsewhere at proofs for other rational numbers.